Welcome to the deep dive. Today, we're diving deep into, well, what may seem like a pretty niche corner of mathematics, linear algebra. But honestly, what we're about to get into is genuinely fascinating, and it has huge impacts, everywhere from supercomputers doing science stuff to, believe it or not, Google's search algorithm.
That's right.
So our mission today is to figure out how these, different ways of looking at the same problem-solving linear equations can actually unlock these really powerful insights. We're focusing specifically on the column picture.
Exactly. The core problem in linear algebra is fundamentally solving systems of linear equations. You often see it written as AXB.
Right.
And, well, historically, there have been two main ways to think about this geometrically, two main interpretations.
Okay, so two pictures. What are they? Let's get those straight before we dive in.
Okay, so the first one is usually called the row picture. If you have a system of linear equations, each equation geometrically defines a hyperplane.
Like a flat surface, but maybe in higher dimensions.
Precisely. So for a simple 2x2 system, that's just two lines on a graph, their intersection point. That's your solution.
Okay, I remember that from school. Two lines crossing.
Yeah, or three planes intersecting at a single point for a 3x3 system. The row picture sees the solution to AXB as that one specific point where all these hyperplanes meet.
And for those small systems, two or three equations, that feels pretty intuitive. You can almost picture it.
It is. It's simple to grasp initially.
Yeah.
But the limitation becomes obvious really fast when you try to scale it up.
Yeah, I can imagine.
Try to visualize, let alone, work with the intersection of, say, 100 hyperplanes in 100 dimensions. Where do they all meet?
Right. My brain just kind of short circuits thinking about that. It's impossible.
Exactly. It's not just a visual problem. It becomes conceptually really messy. You can't really build a scalable understanding around finding that one magic intersection point when the dimensions explode.
Okay, so that's the row picture's big hurdle. How does the column picture get us around this? How does it offer a better way?
This is where it gets really interesting. The column picture is, well, it's more powerful, it scales better, and honestly, it gives you much deeper insight. The core idea is a complete shift in perspective.
Okay.
Instead of hunting for an intersection point, we ask, can we find the right linear combination of the column vectors in matrix A to produce the result vector B?
Whoa, okay. That is a different way of thinking. So
Yeah.
instead of intersections, we're asking, can we build B using the columns of A as ingredients?
Exactly. Think of it like this. You've got a set of basic paint colors, red, blue, green. Those are your column vectors from matrix A. And you want to create a very specific target color that's your vector B. The next vector holds the recipe. The weight's how much of each base color, each column you need to mix together.
Ah, okay. So I1 tells me how much red, by 2 how much blue.
Precisely. The column picture asks, can I mix these ingredients, the columns, in just the right amounts, the weights in X, to perfectly match the target color, vector B? And that question works no matter how many colors or dimensions you have.
That feels much more constructive, less about finding a needle in a haystack. Okay, so that shift, that's the foundation for a lot of modern linear algebra.
It really is. It's not just another viewpoint. It's where many fundamental concepts actually come from. The focus shifts away from, does the solution X exist for this specific B?
Right.
And moves towards understanding the matrix A itself. The question becomes, is this vector B even reachable using the columns of A? Is it within their range?
And that reachability, that's tied to the column space, isn't it? CA. Why is that so critical?
Because the column space, CA, is literally defined as a set of all possible linear combinations of the columns in A, all the vectors you can build.
Ah, okay.
So the implication is direct. A guess B has a solution if and only if that vector B is actually in the column space of A. If B is outside the space the columns can reach, then nope, no solution exists. Simple as that.
So the column space is basically the span of the columns, everything they can possibly create when combined.
Exactly. Span is the term.
Yes.
And then the idea of linear independence comes in. How does that affect whether we can reach any possible vector B?
Good question.
Well, if the columns of A are linearly independent, meaning none of them can be made by combining the others, they all point in genuinely different directions. And if they span the whole space, like Rn for NXN matrix, then yes, a solution exists for every possible B.
So they're versatile enough to build anything in that space.
Right. But if the columns are linearly dependent, if there's some redundancy, like one column is just a combination of others, then they don't span the whole space. They only span a smaller subspace, maybe just a line or a plane within the larger Rn space.
Okay.
In that case, AXB only has a solution if your target vector B happens to lie within that specific limited subspace reachable by the columns.
So it seems like the column picture shifts the focus from B to the properties of A itself. Like, what is A capable of doing?
You've nailed it. It's about the intrinsic properties of the matrix, determined by the geometry of its column space. Things we talk about all the time, like a matrix's rank, or whether it's invertible, or if it can solve for any B. These are all properties of its column space.
Can you connect those, like invertibility and column space?
Sure. For an nxn matrix A, saying A is invertible is completely equivalent to saying A's columns are linearly independent,
Okay.
which is also equivalent to saying A's column space is all of Rn. It means its columns can build any vector B in that n-dimensional space.
And if it's not invertible, if it's singular,
Then A is singular means A's columns are linearly dependent, and A's column space is only a subspace of Rn, not the whole thing. It can't reach everywhere.
So, wow, the column picture isn't just a method for solving axes B, it's the key to understanding what the matrix is and what it does.
Exactly. And this leads us beautifully into something Professor Gilbert Strang calls the big picture of linear algebra.
Oh yeah, I've heard of Strang's 4 fundamental subspaces.
He provides this complete geometric anatomy for any matrix A and is built directly on this column space idea. He identifies 4 fundamental subspaces that give you this holistic view.
Okay, lay them out for us. How do they fit this column-centric view?
All right. First, the column space. We've talked about this. It's the output space, the range, what vectors can A produce.
Got it.
Second, the row space, A. This is the space spanned by the rows of A, or equivalently, the columns of A transpose. Think of it as the effective input space.
Okay, input space.
Third, the null space, A. This is the set of all input vectors X that get mapped to the 0 vector, so X0. These are the vectors that are like destroyed or squashed to 0 by the transformation A.
Inputs that produce no output.
Exactly. And fourth, the left null space.
Yeah.
This is the null space of the transpose. It's the set of vectors I such that A equals 0 A, or equivalently, AG equals 0. Geometrically, it's the space of vectors that are perpendicular to the column space.
Oh, okay. 4 spaces.
No.
And they're related, right?
Deeply related. And perpendicularity is key. The row space is always perpendicular to the null space.
Makes sense. Inputs versus things that get zeroed out.
And the column space is always perpendicular to the left null space. Outputs versus things orthogonal to the outputs.
Okay.
And these amazing relationships between their dimensions, too. The dimension of the column space always equals the dimension of the row space. That dimension is the rank of the matrix,
That's
R.
rank R, okay.
Then the dimension of the null space is NR, where N is the number of columns or input dimension. And the dimension of the left null space is NR, where M is the number of rows or output dimension.
So N is R plus NR, and M equals R plus MRR. The dimensions always add up perfectly.
Exactly. It gives you this complete, elegant, geometric blueprint of what any matrix A does to vectors, how it transforms Rn into ARM.
So putting it all together, we really should see a matrix A not just as this grid of numbers, but as a function, a transformation mapping vectors from an input space R into an output space R.
That's the modern view.
Okay.
And the column picture makes this view so much clearer.
How so?
Because the expression X, when viewed through the column picture, is literally the formula for building the output vector B. It's by 1 times column 1 plus by 2 times column 2, and so on.
Right, the weighted sum we talked about.
It directly shows you how the components of the input vector X act as weights to combine the columns of A to form the output. It reveals the structure of the transformation.
Unlike the row picture.
Yeah, the row picture involves calculating dot products for each row. That gives you the components of the output vector B one by one, but it kind of obscures the overall geometric relationship between A, X, and B. The column picture lays it bare.
Okay, this is making a lot more sense conceptually, but you mentioned real-world impact. How does this abstract idea of a column picture connect to something concrete like, say, high-performance computing?
This is where it gets really cool and surprisingly practical. The abstract choice between row and column pictures actually has a direct physical parallel in how computers store arrays in memory.
Really? How data is laid out?
Yeah. There are 2 main conventions: row major order, which is the default in languages like C, C++O, and Python with NumPy.
Okay, row major.
And column major order, which is used in Fortran, MATLAB, R, and Julia languages, often favored in scientific computing.
Why the difference? And why does it matter for performance? What's the actual impact?
Okay, think about how memory works. It's basically one long line of storage locations. In row major, the elements of a matrix are stored row by row. So element 1, 1, then 1, 2, 1, 3, and so on. For the first row, then 2, 1, 2, 2, 3.
So elements in the same row are neighbors in memory.
Exactly, which is great if your algorithm needs to access data row by row. It reads contiguous memory, which is fast because of how CPU caches work. Caches love predictability and locality.
But what if you need a column?
That's the problem with row major. To get a column, you grab element 1, then you have to jump way ahead in memory to get 2, 1, then jump again for 3, 1, and so on. This is called strided access.
Jumping around. Cache doesn't like that.
Cache hates that. It leads to cache misses, where the data you need isn't in the fast cache, and the processor has to wait while it's fetched from slower main memory. Big slowdown.
Okay, so how does column major help?
It does the opposite. It stores elements column by column. So 1, 1, then 2, 1, 3, 1, down the first column, then 1, 2, 2, 3, 2, down the second column.
Ah, so now the columns are contiguous in memory.
Precisely. So accessing a whole column is now a fast, contiguous read. Perfect for algorithms that naturally work with columns, which are the algorithms inspired by the column picture of linear algebra.
That connection is fascinating. We have a table in our sources, table 1, that lays this out. It really highlights how row major struggles with column access, slow, strided, poor cache locality for AX-type operations.
Right.
While column major is fast for columns, has high cache locality, especially for that AX multiplication, because a whole chunk of a column can fit in a cache line.
And this flows directly into compatibility with high-performance libraries. Things like BLANS, basic linear algebra subprograms, and LPAC, linear algebra package. These are the absolute bedrock of scientific computing.
Right. Highly optimized routines.
And they are typically optimized for column major data, often originating from the Fortran world. If you feed them row major data, you either have to transpose the matrix first, which costs time and memory, or the library might handle it internally, but less efficiently.
And what about GPUs? They're huge for this stuff now, especially AI.
Even more critical there. GPUs thrive on massive parallelism. Column major is perfectly suited for what's called coalesced memory access on GPUs.
Coalesced access?
Yeah, it means that a group of threads running in parallel, like a warp in NVIDIA CAD terms, can access adjacent locations in memory all in one go, one memory transaction.
Super efficient.
Incredibly efficient. If threads were accessing scattered locations like columns in row major, it would require many separate slow memory transactions. So column major data lets column-based algorithms run blindingly fast on GPUs.
So there's this clear pipeline. Thinking in columns, the column picture, leads to column-centric algorithms, which run best on column major data layouts, which are what optimized HPC libraries and GPUs expect. It all lines up.
It's a beautiful alignment from abstract concept down to hardware execution. And it goes beyond just memory layout. Think about CPU vectorization too.
SUM, single instruction, multiple data.
Yep. Modern CPUs can perform the same operation on multiple data points simultaneously using wide vector registers. If your data is laid out contiguously in memory, like a segment of a column in column major format.
You can load that whole segment into a vector register at once.
Exactly. And process it with a single instruction. Huge speed up. Strided access makes vectorization much harder, often impossible.
So both CPUs and GPUs benefit immensely from this column-centric approach, which is enabled by column major storage. That explains why things like matrix multiplication are so well suited to GPUs like the NVIDIA A100s and H100s, which are workhorses for deep learning and science.
Absolutely. Those chips are designed precisely to exploit this kind of data parallelism and memory access pattern, which is inherent in column-based linear algebra.
Okay, but what about really, really huge systems, especially sparse ones where most entries are zero? You mentioned direct methods like LU factorization can struggle because of fill-in.
Right. Fill-in is a major headache. You start with a nice sparse matrix, lots of zeros, easy to store. You try to solve AXB directly, and during the factorization process, boom, tons of those zeros get replaced by non-zeros.
Your sparse matrix suddenly becomes dense and huge.
Yeah, it can blow up your memory requirements and computational cost. For truly massive problems, especially sparse ones arising from things like simulations or network analysis, direct methods are often just not feasible.
So what's the alternative?
Iterative methods.
Yeah.
Instead of trying to get the exact answer in one go, these methods start with an initial guess and then generate a sequence of better and better approximate solutions, gradually converging towards the true solution.
Okay, iterating towards the answer. How does the column picture fit in here?
The core operation in almost all iterative methods is matrix vector multiplication, calculating A times the current approximate solution vector, say AXK.
Which we already established is fundamentally a column picture operation.
Exactly. It's building a vector in the column space. Let's trace the intuition.
Please do.
1. You start with some initial guess, x0. Could be anything, even a zero vector.
Okay.
2. You calculate b0, a0. This is your first attempt at building B, and crucially, B0 is a vector in the column space of A, C, A.
Right, it's a combination of the columns.
3. Then you compute the error, or the residual, R0 equals B, B0. This vector tells you how far off you are, and in what direction within the column space you need to go to get closer to the true target B.
The residual is also in the column space. Wait, is it?
Good question. If B itself is in the column space, meaning a solution exists, and B0 is definitely in the column space, then their difference R0 must also be in the column space.
Okay, got it. So we're always operating within CA.
Always. 4. The algorithm then uses this residual R0 intelligently, and different methods do this differently to pick a better next guess. X1.
I repeat.
5. Repeat. Calculate B1, X1, find the new residual R1, B1, use R1 to find X2, and so on. The hope is that the residuals get smaller and smaller, and XK converges to the true solution.
Are there smarter ways than just following the residual?
Oh, yes. Methods like conjugate gradient, CG, for symmetric positive definite matrices, or GMRES, generalized minimal residual, for more general matrices are much more sophisticated.
How do they work conceptually?
They build something called a Krylov subspace. At step K, this subspace is spanned by the initial residual R0 and the result of applying A to it repeatedly. KK spans 0, R0, A-ish arrow.
Whoa. Okay, what's the point of that subspace?
Since A is in CA and applying A keeps you within CA, this entire Krylov subspace is a subspace within the column space CA. These advanced methods then find the best possible approximate solution, XK, whose corresponding XKK lies within that specific Krylov subspace KK. They essentially project the problem onto this expanding subspace and solve it there, which turns out to be much more efficient.
So they're finding the optimal path towards B within an increasingly sophisticated subspace of the column space itself.
That's a great way to put it. They are performing a kind of guided search within the column space, leveraging the structure revealed by repeatedly applying the matrix A.
It really is everywhere. The column picture underpins direct memory layout, parallel processing, and even these complex iterative algorithms. It's like the unifying language.
It truly is.
Let's make this even more concrete. Part 3. Google's PageRank. This is a classic example, right?
A perfect example of iterative methods and the column picture solving a massive real-world problem.
Yeah.
PageRank fundamentally models the entire World Wide Web as a gigantic directed graph.
Web pages are nodes, links are edges.
Exactly. And this graph gets represented by a huge transition matrix M, sometimes called the Google matrix. An entry meter represents the probability that a user, randomly clicking links, will go from page J to page I.
And that matrix M must be unfathomably large, billions of rows and columns.
Billions by billions, yes. But critically, it's extremely sparse. Most web pages only link to a handful of other pages. So most entries in M are 0. That sparsity is the only reason this is computationally tractable.
Okay, so we have this giant sparse matrix. How does it relate to ranking pages?
The core idea of PageRank is that important pages are those that are linked to by other important pages. It's a recursive definition.
Right, reputation by association.
This leads to looking for an equilibrium state. Imagine a huge number of random surfers clicking around. Eventually, the distribution of surfers across pages should stabilize. Let be the vector where rear I is the long-term probability of a random surfer being on page I. That's the PageRank vector.
Okay, and how do you find ROC?
That equilibrium condition translates directly into an eigenvector equation. The stable distribution R must satisfy Mr. Fair, or more formally, Mr. Fair, where the dominant eigenvalue is 1.
So the PageRank vector R is the principal eigenvector of this massive Google matrix M, corresponding to the eigenvalue 1.
Precisely. It's the steady state of the random surfer process.
Right. But again, solving an eigenvector problem for a billion by billion matrix sounds impossible. How did they actually do it?
Not with direct methods, that's for sure. They used a beautifully simple iterative method called the power iteration.
Power iteration. How does that work?
It's remarkably straightforward. 1, you start with an initial guess for the rank vector, R0. Maybe just assume all pages have equal rank initially, like a vector of 1n everywhere.
Okay, a uniform guess.
2, then you just repeatedly apply the matrix. Calculate RK plus 1 equal M error.
Just multiply by M over and over.
Essentially, yes.
2.
3, after each multiplication, you usually normalize the vector RK plus 1. It goes sample, make its components sum to 1 to keep the probabilities meaningful. 4. You repeat this multiplication and normalization until the vector stops changing significantly. It converges.
And the vector it converges to is?
The principal eigenvector.
Yeah.
The PageRank vector R.
Wow. Why does that work? And how is it the column picture?
It works because repeated multiplication by m amplifies the component of the vector corresponding to the largest eigenvalue, which is 1 here, relative to other components. And it's a direct application of the column picture. Each multiplication m yo-yo k is exactly a linear combination of the columns of m, weighted by the current estimated page ranks in ARM.
Ah, right. Mio is the probability of going from J to I, so column J of M represents where a surfer on page J might go next.
Exactly. Multiplying m by RAK simulates one step of all of the random surfers moving simultaneously. It distributes the current importance across the network according to the link structure encoded in the columns of m.
That's incredibly elegant and computationally feasible only because M is sparse, right?
Absolutely crucial. That multiplication MUR doesn't involve billion squared operations. It only requires operations proportional to the number of non-zero entries in M, the number of links on the web. That's what makes it possible.
Amazing. Okay, so from hyperplanes to HPC to PageRank. Now for our final part, let's push even further. Part 4. Quaternions. This feels like a leap into abstract algebra. Does the column picture help here too?
It absolutely does. Quaternions are fascinating. They extend complex numbers to 4 dimensions. Q, ATS plus E plus Cavia plus EK. The twist is the multiplication isn't commutative, IJK, but GSK.
Right.
And I blot by AT goes Ishi R1 8, Thopling's Ecto 1's 1.
I remember hearing they're used a lot in computer graphics and robotics for 3D rotations.
That's their killer app. They offer big advantages over using 3x3 rotation matrices. They're more compact, 4 numbers versus 9, and over Euler angles because they avoid gimbal lock and allow for smooth interpolation between orientations.
Okay, how do they represent rotations? You mentioned pure quaternions for vectors.
Right. A 3D vector v, vx, vi, vz, is represented as a pure quaternion p equals 0 plus vx's plus vj plus vck. To rotate this vector p using a unit quaternion q, where q1, you use this operation called the sandwich product, p equal qp quick, where quick is the inverse or conjugate for unit quaternions.
That qp quick looks algebraically intimidating. How can linear algebra, the column picture, possibly simplify that?
That's the magic. The key is to realize that quaternions themselves can be treated as vectors in a 4-dimensional space.
Just map qss plus I plus yj plus ek to the vector sxyz.
Exactly. Once you do that, lots of quaternion operations become standard linear algebra operations on these 4D vectors. Quaternion addition, just vector addition. The norm squared, just the dot product of the vector with itself. The conjugate q, which is sxiy_jck. That's just applying a simple linear transformation multiplying by a diagonal matrix diag 1 on is 1 on is 1 upon me.
We have table 2 in the sources acting as a Rosetta Stone. It maps quaternion concepts to linear algebra. So quaternion net of authority vector, conjugate linear op. What of multiplication? That's the tricky one.
Multiplication is the linchpin. Turns out left multiplication by a fixed quaternion, say L, is a linear transformation on the 4D space of quaternions. Any linear transformation can be represented by a matrix.
So multiplying by L on the left is equivalent to multiplying the 4D vector by some 4x4 matrix. Let's call it ML.
Precisely. And the columns of that matrix ML are easy to find. They're just the results of left multiplying the basis quaternions, 1ijk by L, and writing those results as 4D column vectors.
Okay.
Similarly, right multiplication by a fixed quaternion R is also a linear transformation, represented by a different 4x4 matrix MLR.
Whoa. Okay, so left and right multiplication are just matrix multiplications in this 4D space.
Yeah.
How does that help with the p quaterny rotation?
Now you can translate it. P key means first right multiply P by Q, apply matrix MR to P vec, then left multiply the result by Q, apply matrix MLQ to the result.
So P vec appalls MLQ, MRQ, P vec.
Exactly. And matrix multiplication is associative, so you can group it as P vec, MLU, P key, MRQ, P.
Wait, so that whole complicated sandwich product is just equivalent to multiplying the vector P vec by a single 4x4 matrix. Muller, MLQ, MRQ.
That's it. Quaternion rotation in 3D is just a linear transformation in the underlying 4D space, fully captured by a 4x4 matrix derived directly from the quaternion multiplication rules, which themselves are built on the column picture idea when constructing ML and MR.
That completely demystifies it. It makes quaternions feel much less alien and connects them straight back to standard linear algebra. The column picture provides the bridge.
It does, and it goes even further. This extends to general rotations in 4D space itself, which are sometimes called double rotations or isoclinic rotations.
Rotations.
Yeah. A general rotation in 4D isn't a sandwich product. It's represented by multiplying a 4D vector P by two different unit quaternions, one on the left and one on the right. PSELPR.
Okay, LPR. How does the matrix view handle that?
Elegantly. Using our matrix representations for left and right multiplication, it just becomes PVEC equals ML MR PVEC.
Yeah.
Or simply PVEC ML MR PVEC.
So a general 4D rotation corresponds to applying the matrix product of the left multiplication matrix, ML, and the right multiplication matrix, MR.
Precisely. It shows that the two independent components of a 4D rotation, called left isoclinic and right isoclinic, correspond directly to the linear transformations represented by left and right multiplication by two unit quaternions.
That's incredible. The column picture as this universal translator, again, letting us use familiar matrix tools to understand the geometry of this more abstract algebraic system. It really ties it all together.
It's a remarkably unifying concept.
So let's try and wrap this up. We followed this thread, the column picture, through this whole deep dive.
Yeah, we started with it just being a different way to view XB, but saw how it defined fundamental concepts like column space, span, linear independence, and rank.
Right, the foundation.
Then we saw its very physical manifestation in computer memory layouts, row major versus column major, and how that impacts performance in HPC, enabling efficient CPU vectorization and crucial GPU coalesced memory access.
From abstract idea to silicon.
Then its role in making iterative methods work, operating within the column space via matrix vector multiplies, solving huge problems like PageRank, using power iteration, which is pure column picture action.
Billions of web pages ranked.
And finally, seeing it act as a lens to understand and operationalize even abstract systems like quaternions, translating their operations into standard matrix linear algebra.
It's quite a journey for one idea. So the big why you should care for our listeners, why does understanding the column picture matter?
Look, it's not just, an academic curiosity. It's genuinely a fundamental part of the toolkit for anyone doing modern computational science, data analysis, engineering, machine learning, anything involving large data sets and transformations.
It's a way of thinking.
It's a consistent, scalable framework for thinking about these problems. It helps you understand why certain algorithms work, why certain hardware is fast, how different mathematical tools connect. It lets you see the underlying structure where others might just see equations or code.
So a final thought to leave everyone with.
Maybe next time you use a search engine, or see a 3D graphic rotate smoothly, or even just, run some data analysis, take a second. Think about the transformations happening underneath. Are they just crunching numbers?
Okay.
Or are they fundamentally about combining columns, about building new possibilities from existing components within a defined space? How many other complex systems out there might secretly be running on this elegant, powerful column picture logic, just waiting for us to see them that way?
Yeah.
What could you build or understand differently by thinking in columns?